Okay. Can you guys hear me? Hello? Okay. So let's, okay, let's get started. Yeah. So yeah, first I'm sorry that my COVID symptom is still there. Okay. I don't feel anything, but the test kit shows that, I mean, still shows show 2 lines. So because of that, I think it's better that, I mean, I keep our lecture online. Okay. Yeah, I was surprised. I mean, for the, you know, the COVID to stay this long, but I hope like I mean the situation will improve like in the next few days, and we will be back to the regular lecture next week. Okay. Again, okay, please check your email, okay, to verify if there's any change, okay, for the lectures situation. Okay, I hope we will move back to like a regular lecture, okay, next week. But just in case if there's if my situation, the COVID-19 situation prolongs, then, you know, we may still need to you know, do it online. But I really hope that's not the case, okay, because it has been, you know, 2 weeks, okay, more than 2 weeks, okay. You know, if we, I mean, count, because the first time I found my I have COVID was like last Tuesday, so it has been like more than a week by now. But if we, I mean, next Wednesday is going to be much longer than 2 weeks. So supposedly, you know, I should get, you know, back to normal. Okay. So yeah, back to the lecture. Okay. Oh yeah. Before the lecture, okay. One more thing to talk about. Okay, because some students reflect to me that the final project, okay, the term project wasn't posted, so I have especially asked the TA to post the term project, because I actually sent out the term project with the homework 3 to the TA, but somehow only homework 3 was posted initially. The TA didn't post the term project, so I asked them to do that. And also, some students asked me like, how many students form a team? Okay, I believe currently our morning session, we have like about 50 to 60 students. Okay, I know some students dropped because I signed some forms, but I'm pretty sure we should still have more than 50 students. If that's the case, okay, considering like each group will have at least like 10 to 15 minutes of the presentation time, okay, I think it's probably a more realistic to ask like 3 students to form a team, okay. This way we have like 15 to 17 students, 15 to 17, about 17 groups. 17 groups. If each group is like 10 minutes, it's like close to 3 hours. Okay, so yeah, so let's set it to be 3. Okay, for 3 students for each group. Okay, I know some students have already looking for the teammates, which is nice. Okay, and I also want to remind you that your teammate information needs to be submitted along with your homework 3. Okay, if you didn't do that, then the TA is going to assign the teammate for you. Okay, which obviously may not be a good idea. Okay. Okay, so back to the class. Okay, so last week, okay, we talked about the issue with like a strong correlation between 2 variables, to be exact. We have this sorry. We have this this example. Okay, intentional, that I mean there are this one. Well, this examples data set that was intentionally created, and we try to make x1 and x2 highly correlated, and as a result, you'll see like if you put like both x1 and x2 in the model, you the model will become very difficult to tell the impact of x1, x2. That's because like pretty much that shoot. Okay, let me just yeah. Yeah, it's difficult for me to control like yeah, the slide. Okay, so now okay, it's better. So that's because of the confounding variable, okay, effect, okay, and where am I? Wait. And yeah, if you try to analyze it, okay, and you know, the Bayesian data analysis will give you this result where beta 0 and the beta 1 are pretty much like you know, if you increase one, the other one decrease. That's because the x1 and x2 are pretty much identical, so you can rewrite the formula like the lower one, and eventually, okay, it's the beta 1 plus beta 2 that is the constant, instead of like the beta 1 and the beta 2 separately. Okay, so as a result, we end up with this figure, which obviously is not a good idea. Okay, it's not ideal. Okay, so so we talk about this, and we mentioned about like you know, when the correlation is really of your independent variables are really high, okay, then okay, it is going to be an issue, okay. But how high do we consider the correlation to be high? Okay, if it's higher than 0.9, something like that, then we probably don't want to put them together in the model. Okay, we want to, you know, sort of like you know, change the way. Okay, change the, I mean, maybe just use one of them, or you know, find another way to deal with that. Okay, so if the correlation is really high, as I said, we eliminate one of the variable. But you may ask, which variable to eliminate, right? So the variable that we eliminate, okay, it could be based on the convenience. Okay, what do we mean by the convenience? Okay, basically, okay, you can remove the least known variable, okay, in this problem, okay, or okay, the variable that is difficult to explain, more difficult to interpret, okay, then you, I mean, if that's if you have two variables and one is more difficult to interpret, then you remove that variable. Okay, so in some sense, like you want the remaining model to be easy to explain. Okay, that is the most important you know, reason. Okay, we use the Bayesian data analysis anyway. Okay, so another way to deal with this okay, is to create a new variable, okay, that and to replace those two variables with a new variable, okay, and there are different ways to deal with that. For example, you can do the dimensionality reduction. There are many ways to do dimensionality reduction. One of the most well-known algorithm is called PCA, okay, Principal Component Analysis, okay, and the PCA can be done by one line of code, okay, very, very straightforward, okay. So by using one variable, okay, or in some sense, you pretty much reduce those multiple variables into one, okay. But the issue is, okay, this new variable, this that you obtained by the dimensionality reduction, most likely will be a linear combination of the original variables, right? So so it will become an issue when you try to explain this new variable, okay. So on one hand, it's a convenient way to reduce multiple variable into one, okay, by using dimensionality reduction. On the other hand, it makes the interpretation more difficult, okay. So there's a pros and cons, okay. And the third way to deal with this is to put strong priors to reduce, restrict the plausible value of the coefficient, okay. So in the later chapter, okay, we will talk about this approach, but yeah, as I said, we may not have time to talk about that chapter. You can check it out. The subject, the title of this discussion is called regularizing priors. Okay, regularizing priors. So that another interesting, okay, phenomenon, okay, is like this. It's called the masking effect variables. Okay, in the previous example, it's kind of like we have too many variables because some variables are highly correlated, right, and which cause the issue, right? But in some other case like this, okay, this masking effect variables, you can sort of think of this as like exactly the opposite of the previous problem. Okay, so what is this? Okay, if you have this situation, okay, like the independent variables are positive correlated to each other, but they are also correlated to the dependent variable. Okay, so that's we have x1, x2. They are positive correlated, but they are also, they are correlated to y in the opposite directions. Okay, so one is positive correlated. Okay, the other one to y is negative correlated. Okay, you may ask, can this happen? Yes. Okay, it is possible, but of course, like it's relatively difficult to rare to see such a case, okay, in nature, okay. So we intentionally create a data set here, okay. So here you see, we set a random seed and create 126 point, okay, and x1 you see we randomly generated, and x2, okay, is x1. We use x1 as the mean, and then we try to add some random numbers to it to make x2 and x1, okay, somewhat correlated. And then, okay, y is, pretty much x1 minus x2. Of course, again, we put some randomness into the result, but you can see that, okay, y is correlated positively to x1, but it's correlated negatively to x2, right? And then we put the x1, x2 together, and we draw the figure. They look like this. They may not look so easily to you that, for example, like x and y, sorry, x1 and x2 and y are, positive correlated, but the x2 and y are negative correlated, because you see they scattered pretty randomly. But if you try to compute their correlation, you will see that, yes, one is positive correlated, the other one is negative correlated. So, okay, so after we create this data set, let's try to, again, use those three models to show what happens. Okay, the first model incorporate like a multiple linear regression. Okay, we have x1 and x2 both in the model, and for the second model, we use a simple linear regression. In other words, we only have x1. Okay, in the third model, we have only x2. Okay, so after going through the same process, here is what happens. And once again, the model x1, x2 has like a beta 1 and beta 2, but the model x1 only has beta 1, and the model x2 only has beta 2. Okay, so you can see that, okay, it shows that, okay, oh, by the way, remember, like I mentioned, like the previous figure of this kind has some issues, right? But this one is correct. Okay, this one is correct. Okay, so I don't know what happens. Why they generate like a wrong figure in the previous example, but this one is not, doesn't have problem. Okay, so you can see the average, the mean of the beta 1 and the beta 2 in the model mx1, x2. Okay, one is near, beta 1 is near 1, and the beta 2 mean the beta of beta 2 is near -1, right? which is obviously the case if you consider how we create the y, right? So obviously, okay, in this example, okay, when you include x1, x2 in the model correctly capture the coefficient, okay? But interestingly, okay, if you only include beta 1 or, x1, or if you only include x2 to do a simple linear regression, then your beta 1 and the beta 2 will be their mean will be very close to 0. Okay. So why is that? Okay. So first, okay, I will have to say that obviously the model x1, x2 works pretty well, okay, because you know it matches how we created the data pretty well, okay. But the issue that you know remaining only x1 or remaining only x2, okay, doesn't have a very good analysis result is because somehow, okay, the effect cancel out each other, okay? The effect cancel out each other because y actually is, you see, in some sense, because x1, x2, even though they you know, we add some randomness to them, but you can see that y is, you know, obtained by x1 minus x2, right? So, you know, even though, and we know x1, x2 are positive correlated, right? So in some sense, okay, you could say that these two numbers are, you know, close, right? So when these two numbers are subtracted, I mean, to each other, so their effect will reduce. Okay, their effect to y will reduce if you only have one variable remain. Okay, so this is the issue. Okay. So x1 is correlated to x2. So when x1 increases, x2 also increases. Okay. So when y increases, x1 also increases, but x2 decreases. Okay. That's, you know, based on our the creation of how we create the data. Okay. So as a result, okay, we get a partial cancellation of effects unless we include both variables in the same linear regression. So this is the problem, okay, of the, you know, masking effect variables, okay. So in the previous confounding variables, okay, we have two variables that are highly correlated, and we need to get rid of one somehow, right? And in this example, I mean, we have two variables. They are also positively correlated, but they are negatively correlated to the dependent variables. Then in this case, both have to be there. Okay, notice that, okay, if you include beta X1, X2 in the model, okay, your model works. They can be used for your model can be used for prediction. So everything, I mean, is fine in your model. But the issue is it's exactly opposite. Okay, if you include only one of the variables, then we have a condition. Okay, we have an issue. Okay, so this cancellation, okay, will make the simple linear regression of either X1 or X2. Okay, no, with a very low coefficient, mean, which doesn't represent the situation pretty well. Okay, so so this is as I said, kind of like the opposite of confounding variable. Okay, so again, okay, the reason I show you these two examples is to tell you to choose your variables wisely, or independent variable wisely. Okay, it's not like you should put everything into the model, but on the other hand, okay, you should not like avoid putting some important variables. Otherwise, your the result of the analysis may not be correct. Okay. Oh, and by the way, obviously the X1, X2 in the previous example, I mean, they are positive correlated, but not like a very highly positive correlated. If they are highly positive correlated, then we have that confounding variable issue, right? So so it's difficult to when the coefficient, when the like correlation is higher, which effect is more serious. Again, that require certain experiments, okay, and see like which model will end up with a better interpretation, like interpretability. Okay. So anyway, okay, so let's move on to the next topic. The next topic is the what we call like interactions. Okay, so here, okay, now I mean in the multiple linear regression, okay, we have like multiple variables, right? X1, X2, for example. Okay, but sometimes you will find that, okay, the data behavior is not linear. Okay, it's not linear. Okay, so for example, okay, is you can see the effect of, actually this happened in many real world situations. Okay, so for example, like the effect of drugs. Okay, increasing the dose of one drug, normally if it result in positive effect on the patient, okay, but if you try to put like both drug, okay, the drug A and drug B, okay, to the patient, then it may make the drug A, the first drug, okay, I mean, a negative like impact to the patient. Okay, so putting two medicines together to a patient is very difficult choice for the doctor. Actually, I believe the doctors like training in the you know in the school, okay, you know, spend a lot of time on this type of stuff, like which drugs are compatible. They can be prescribed at the same time to the patient. Which drugs are incompatible. You should never prescribe these drugs together to a patient, okay? So there are all this type of like, you know, nonlinearity, okay, between different type of drugs, right? And we see examples like this, I mean, you know, in our life as well, okay? A lot of time, like you see, if you see two variables, okay, in a real world problem, normally the impact of these two variables are not necessarily linear. Okay, of course, like if they are roughly linear, we will use the, you know, the linear model, which is normally good enough. But if they are, you know, the result is not linear, okay, to a certain degree, then what do we do? Okay, we could put the interaction term into our formula, okay, something like this, okay. Here you can see, okay, the mu, okay, equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2. Okay, this x1 times x2 obviously is a non-additive term, okay? And in statistics, we know this term as what we call interaction, okay? So, of course, you could have many different types of interactions, okay? For example, okay, you can have x1 square x2. You can have x1 x2 square. You can have all sorts of interaction between x1 x2, okay? But for simplicity, we are going to restrict a discussion to only the multiplicative case, okay? This x1 x2 only, okay? So if you create a linear regression like what we have previously, then you can put together the second and the fourth term, and you know, try to get the x1 out of, you know, the common term x1 out, and you will see that, okay, it becomes like what should I say, a linear equation inside linear equation, okay, something like that, because beta 1 plus beta 3 x2 will become slope of x1, okay. And obviously you can put the third term and the fourth term together, and you know, try to, you know, get the common term x2 out of it, and it looks like the lower equation. And in this example, in this case, the beta 2 plus beta 3 x1 will be the slope of x2, right? Obviously, these slopes are not constant, okay? I mean, they change when the corresponding variable is different, okay? So you can see that such a regression, okay, obviously, okay, has multiple ways to explain it. So it's the linear model with interactions is not easy to interpret. Okay, it's not easy to interpret. This is here. I mean, we use like we show like you know, we try to put the interaction term you know, like this to to explain that as either slope of x1 or slope of x2. It's just like try to explain one way to explain it, but obviously like there are much. There are other ways to do it. Okay, so it is complicated. So the interaction term, okay, can be understood as linear model. Okay, so we still use that. Okay, we still call that as multiple linear regression. Okay, it's just like it has like a interaction, okay, between the variables. Okay, so the interaction in the example that we shown is symmetric. Okay, so in the sense that we can think of it as slope of x1, okay, as a function of x2, or we can think of it as a slope of x2 as function of x1. Okay, so it's symmetric because the equation, this original equation is also symmetric, right? So it's an interpretation. Obviously it's symmetric. So in multiple regression model, without the interaction, we have a hyperplane. Okay, very simple, like a linear model give us a hyperplane in a multi-dimensional space. Okay, but if you have an interaction term, so it will create a curved surface. Okay, so it's called hypersurface. Okay, there's a curvature. Okay, for this surface. Okay, this is just because the slope is not constant, as I have shown you by these two equations. Because slope is not constant, so it keeps changing, which will produce the certain curvature. Okay, and the coefficient beta 1, okay, describe inference of predicting x1. Okay, only at x2 equal to 0. Okay, because otherwise, you see in this equation, not only beta 1 affect like the result, but also beta 3 also has impact, right? But when x2 is 0, okay, the third term, the fourth term are eliminated. So it goes back to the simple linear regression case. So we can have an easier explanation. Okay. The same can be said, okay, for beta 2. Okay. So beta 2 describes inference of predictor x2 only at x1 equal to 0. Okay. For this interaction, we could have an example, but we don't. Okay. I think the result will be very. If we have an example, it's going to be very simple. Okay, very simple. But the issue is like because it's higher dimensional. Okay, so it's difficult to be observed. Okay, especially when the surface is like has curvature. Okay, so the next topic, which is the last topic of this chapter, as I said, after we finish this chapter, we will move back to the MCMC. Okay, So well, it's 9:50 already. Let's take 10 minutes break. Okay, we come back. We'll continue from here. Okay, variable variance. Okay. Okay. Let's get started. Okay. So in all previous regression model, linear, okay, of distribution, okay, in order to fit the set, right? But we also know sometimes the variance, okay, or standard deviation can also change, okay, in in a linear way, okay. So equation to model the standard deviation, okay. So which pretty much is you know, no never a problem, okay, in the Bayesian data analysis, okay. So as an example, okay, let's consider, okay, the baby's length when just born, okay. We normally will measure of the baby and the weight of the baby to see, you know, its percentile. Okay. Basically, the WHO, you know, has a statistics of like the baby, you know, data on all people all over the world. So, for example, like when a baby, newborn baby is like, you know, has a certain, you know, height. Is this height, you know, you know, reasonable? Okay, is there any like, you know, problem with this height? Maybe it's too short, or maybe it's too high, too tall. Okay, so basically, okay, we can tell, okay, the baby's condition from this percentile. Okay, just to show you the how it looks. Okay, you can check out this website. Okay, www.who.int. Okay, /child growth /en. Okay, that's, I mean, obviously like the English version. They are, I mean, this is like done in many different languages. So the data set for the looks like this. Okay. So for each month, you can check if your baby, okay, is in what percentile. Okay. For example, if your kid is in 99 percentile, that means he or she is okay, it's a huge one. But if your baby is like below 50 percentile, that means your baby is below average. But obviously, it's just below average. Mean like any the baby grows statistically. Okay. So if the kid like if a baby like the percentile, okay, keep dropping, okay, month after month, obviously there's an issue. Okay. If the dropping is not, if this percentile drop is not, is gradual, then it's never a problem. Okay. I'm talking about like if it's a sudden drop, then we have an issue. The reason is because for Asia people, I mean, remember this is this data set is done by people all over the world, right? So like for Asian baby, okay, for Asian baby, when the newborn, okay, I mean when Asian, okay, okay, will have 99 percentile in weight in a lot of categories, okay. But you know that like Caucasian and black people, they they actually like they average height is sorry, wait, wait.哦，OK，OK，OK，OK，好，等我一下。Yeah, sorry. I mean, according to TA, it looks like the slide. I mean, I showed you. I mean, wasn't working. I mean, how about now? Is it is it okay now? Okay. So yeah, I was talking about like the babies like percentile. Okay, for Asian baby, like when the baby was newly born, okay, normally like the Asian baby has tend to have like a very high percentile, like 99, okay, percentile. But I mean the Asian people. Hmm?喂，还是怪，我重新分享啦。等一下，我刚刚重新分享了，等一下，我再试一次。 Okay. Yeah. Sorry. I mean, there was some technical issue. Okay. Now hopefully it has been resolved. Okay. So here is the, babies like a, length statistics. Okay. Of course, it's the x-axis. I mean, represent the months of the baby, and the y-axis represent the distribution of the length. Okay. And yeah, I was talking about like the Asian baby tend to be like at the top percentile. Okay, when the baby was newly born, but we know like Asian people tend to be shorter on average than like Western people. So this percentile, okay, will gradually gets reduced. Okay, but because like here we are talking about like a newborn, like maybe like 2-3 years old at most. So pretty much like you don't see much difference in height between different races. Okay, but of course like the as like I mean the age gets older, you will see like the Western people grows much faster, like especially in the teenager period of time. Okay, so but anyway, okay, just want you to understand, okay, what is this percentile mean? Okay, and I also want to point out like this distribution of the height obviously will increase gradually, right? For example, like when a baby was newly born, okay, yeah, I mean we have some variation in length, but it shouldn't be too much difference. But as the kids grows to like 2-3 years old, you will see this, the length, okay, can become more and more diverse, right? So this is a very natural example to show you that the variance should not remain a constant, okay, to the months, okay. In other words, the month, okay, as months goes by, okay, the variance of the height should increase, okay, and this increase can be modeled in our, it can be embedded in our model, okay. So let's see how we deal with it, okay. So first, okay, this is a code, okay. The alpha, beta are obtained from a normal distribution with standard deviation 10. Okay, obviously these are the prior. Okay, and then okay, we have another set of variable called gamma and delta. Okay, they are half normal. Okay, with standard deviation 10. So for alpha, beta, gamma, and delta, they are all very vague. They have all have very vague priors, obviously. Okay, and we have this shared variable, okay, which is the data dot months dot values times 1.0. So this is this x share basically equals to the months dot value. But obviously, I mean, you can see that we try to, because this month start values is integer, so we intentionally multiply this value by 1.0 to convert it into you know, a floating point number. Okay, and then okay, mu which stands for the mean of our you know, regression. Okay, so it's going to be alpha plus beta times x share. Okay, to the power of, you know, 0.5. Okay, so in other words, this is not a simple linear regression. This is you know, alpha plus beta times square root of x. Okay, instead of just a simple x, we put the square root of x there. Okay, so it's just a simple trick to fit a linear model to a curve, because like this is actually a curve. Okay, of course, like this is if you use a linear, okay, if you use like a x share to a power of 1, okay, in this place, then I mean, it's just going to perform poorly. Okay, I'm not saying it's going to be it's not going to work. It's just, you know, it's because like we know, okay, I mean, this is like a known example, so we use like a square root of x here. Okay, but if you don't know, okay, better, if you do not know better, maybe obviously you would just use a simple linear function here, which is, you know, which work, but because the result may not be good, you may want to go back to consider you know, adjusting something in your model. Okay, anyway, so this is mu. Okay, and we have epsilon. Okay, which usually is a very simple. We just get it from a prior, but now, okay, it's different. Okay, we assign this epsilon with gamma plus delta times x share. Okay, so this epsilon, okay, which normally represent like the standard deviation. Okay, now, okay, it also has a linear function to it. Okay, and then we put this you know, into a normal distribution. Okay, mu equal to mu, standard deviation is this epsilon, and then observed equal to data length. Okay, yeah, I believe there's okay, and then we try to fit this data set, okay, by generating like 1,000 samples. Okay, and we use the following figure to show you the result. Okay, the mean of mu is represented by the black curve, and we have two semi-transparent region. Okay, the inner region represent like the, you know, just one standard deviation. Okay, the outer region represent like 2 standard deviations. Okay, so you can see the standard deviation, okay, increases, okay, along with the month. Okay, so again, this is natural. Why? Because like when kids grow, okay, their situation will diverge, right? Some family give like more food, some family give like less food, some family, you know, do something to the kids, some family do not. Okay, I'm not saying that kids get abused. I'm just saying like, it's just like a different family raise the kids differently. So initially, okay, they may not have such a large, like standard deviation wise. It may not, the difference may not be that much. But I mean, as time goes by, the kids becomes like more and more diverse in terms of height. Okay, but the author, okay, why the author, is interested in this example? It's because at the writing of this book, the author had a newborn daughter. Okay, I mean, his newborn daughter is 2 weeks old. Okay, about like half a month. So the author is interested to know if his daughter's percentile. Okay. However, remember the month in here in the data set is is integer, right? So because his daughter is like a 0.5 months, which is not an integer, it actually is actually like the primary reason we introduce this X shared variable. Okay, because to be honest, okay, at least like based on the data set, okay, you really don't need this X shared variable in the model. You can just use the data.month.value, okay, and it should work pretty well. But the reason to introduce this X shared is that so that you can, you can here, okay, you can set this variable to be 0.5 months, and then use sample posterior prediction to generate samples to check the author's daughter's percentile. Okay, so first you set this X shared that to use X set value, okay, to set X shared to be 0.5, and then you use the sample posterior predictive to generate like your samples. I mean, 2,000 to be exact, and then you try to draw it to see like the result. Well, I mean, here is like you just assign that to PPC. You haven't drawn it yet, okay? And here is the place you really draw it out, okay? And the author's daughter is here, right here. So his percentile is 59, okay? A little bit above the average in terms of the height for a half-month-old baby. Okay, so that's about it. Okay, any question for this chapter? Okay, if no question, okay, yeah, that's about 1.5 lecture. Okay, I hope like yeah, nobody asked question, right? So if no question, I will move on to the next set of slide. Okay, give me 1 sec. Can you guys see the slide? Let me know if you have any problem, with like the slide. Okay. I hope like yeah. Okay. Good. So let's continue. Okay. So this here I'm intended to introduce how the sampling is done. Okay, this is as I say, this is crucial to the development of Bayesian data analysis. Okay, so the set of algorithms that help sampling is called MCMC algorithms. Okay, so it is obviously the MCMC algorithm and the fast computer hardware that allowed us to do Bayesian data analysis. That's where you just hit the magic button for the inference. Okay, regardless how complicated your model may look like. Okay, with like the help of the hardware and this MCMC algorithm, you are able to to draw the posterior very easily. Okay, so actually, okay, this would this is not possible like just like 30 years ago. Okay, in other words, like the MCMC algorithm was like really developed like in the late 80s, early 90s. Okay, so in a long history of mathematics, the MCMC algorithms are really new. Okay, really new thing. Okay, but of course it has a long and lasting impact. Okay, so for realistic applications that neither have appropriate conjugate prior, nor can be solved using dense grid of points for prior distribution. Okay, MCMC method reduce the accurate approximations to Bayesian posterior distribution. Okay, produce. So it is able to efficiently generate the posterior distribution. Notice my word, efficiently. Okay, because obviously if you use grid points, you can always generate the prior distribution. It's just like remember like if your model contains like tens or even 20 or even more than 10 variables, independent variables, then grid points, okay, even if you only have like a 10 point per dimension, it's going to grow, exceed the computer's computing power. Okay, so so how do we do it? So there are some assumptions that we have to have for any MCMC algorithm. Okay, the first one is the prior distribution is specified by a function that's easily evaluated. Okay, which is normally the case. Okay, we always specify the prior. Okay, and the prior is normally obtained from a very simple, probability distribution, okay, which can easily be evaluated, okay. So if you specify a value for theta, okay, P of theta can easily be determined, okay. So value of the likelihood function P of D on condition of theta can also be computed for any specified value of D and theta. So this is your likelihood function, okay. As I said, I mean, the likelihood function is one part of your model, okay, which has to be defined, okay, okay, and the definition has to be in a form such that it can be evaluated easily once the data and the theta are given. I mean, keep in mind that I mean, P of D is difficult to evaluate, but P of D on condition of theta, okay, this likelihood in most cases are very easy, easy to evaluate, okay. For example, like if you flip a coin, okay, say the theta is 0.5, and the probability of coming up like 3 straight heads, well, this probably can be easily, calculated, right? So this type of stuff, these two assumptions are very important. So we call this algorithm MCMC, right? So what is MCMC? Okay, the first MC stands for Monte Carlo. Did I explain the meaning Monte Carlo to you guys? Monte Carlo is the most famous gambling city in Europe. Okay, it's I believe it's in somewhere in France. Okay, and just like Las Vegas. Okay, because nowadays like people, when we talk about gambling, we say it's Las Vegas or like Macau, but in the old days, okay, when US is still not, when US, is still, what should I say? I should say when Europe is still the dominating power in the world. Okay, I'm not talking about like very, long time ago. I'm just talking about like about maybe before the World War II. Okay, so like about, well, that was 1940, right? So about like 80 years ago, okay, 80 years ago, okay, the world order is totally different, okay, from now, okay. So people, okay, all the research work were published either in Germany or in French, okay. So people, tend to, learn the language people learn are, the language in Europe, okay. And because of that, okay, a lot of terms used in the finding will be, will have something to do with the Europe, okay. So for example, this Monte Carlo, okay, Monte Carlo refer to pretty much just a random process, because Monte Carlo, as I say, is the biggest gambling city in Europe. okay, or I probably should say like it's the biggest gambling city in the world, okay, back to the old days, okay. So that is why, okay, people called random prop, because in gambling place, I mean, you throw a dice, you do some, any gambling pretty much is about random event, right? So I mean, so we naturally named like random process after Monte Carlo. Okay. So here we want to approximate distribution with a large amount of sample. Okay. The fundamental is this concept of representing distribution by a large representative sample, such as pool and surveys. Okay. But random is subset, sampling a subset of people from population. We want to estimate the underlying tendencies in the entire population. Okay, so we do this all the time, right? Like before the election, we do a poll to see like who is winning, right? Which candidate is winning. Okay, so for this type of like a survey or pool, okay, the larger the population, the better the estimation, obviously. Okay, so the population from which we are sampling, okay, is defined as a distribution, okay, mathematically, okay, such as posterior probability distribution, okay. So we want to sample from posterior probability distribution. Okay, so example to show you, okay, you can see, okay, this is a distribution, okay, on the upper left corner, this is distribution. If you use like 500 samples to simulate it, you will see it is not very smooth, right? Not very smooth. It has like edges, like all over places. Okay, and you get the mode to be 0.723. I mean, compared to the 0.7 mode in the theoretical value. Okay, this is obviously this approximation is obviously not good. That's because we only have 500 samples. But when you increase the sample to, for example, 5,000, you see the distribution becomes much smoother, and the mode becomes much closer to the 0.7, right? And you could increase this 5,000 to 50,000. Okay, once you increase the scale of your sample, okay, by another order. And obviously here you can see the distribution is very smooth to say the least. And the mode, okay, is getting even closer to the real one. This is actually a very good approximation already. Actually, I probably should say like, even with the 5,000 samples, the result is already pretty much, it's already very close to the real distribution, okay? Because you see the difference between 7 and 0.696 is only 0.004, right? So it's less than 5%. Well, probably a little bit more than that 5%, maybe 7-8%. Okay, but you get an idea. This is all these are, as long as you increase the sample size, okay, the approximation can be done very well, okay? So that's the idea of like using the sampling technique to approximate a distribution, okay? But obviously, like when you have so many variables, that means like your distribution, is your random variable, okay? Sorry, independent variable. The dimension is so huge, and the combined space of your independent variable is so huge. How can we sample a large number of representative values from a distribution with such a large space? Okay, as I said, like a grid-point approach doesn't, it's not effective enough, right? So we can ask such a question to a politician. Okay, what do we mean? Okay, let's suppose, okay, an elected politician, okay, lives on a long chain of islands. Okay, we assume his territory is a long chain of islands. Okay, so he is constantly traveling from island to island. Okay, because he's a candidate for the next election, right? So he wants to stay in the public eye. Okay, he wants everybody to see him, to know who he is, so that like in the next voting, he can get more number of votes, right? Okay. So at the end of a grueling day of photo opportunities and fundraising, okay. Oh, by the way, in US, okay, the campaign is always about photo opportunity, photo taking, and fundraising. Okay, it's very different from Taiwan. In Taiwan, like you see, like candidates just go everywhere to shake hands, right? Shake hands. But in US, you don't see that very often. Okay, so basically just like a photo taking and fundraising. If you support a certain candidate, you donate to that candidate. Okay. So anyway, so this petition has to decide, okay, a few things at the end of the grueling day. Okay, first, stay on the current island. Okay, obviously, this petition must be on one of the island at this moment, right? So he needs to decide whether or not to stay here. Okay, if not, he has two choices. One is move to the adjacent island to the west, or move to the adjacent island to the east, right? So, well, we only have this, let's assume we only have these three options. Okay? So, what is our goal? Our goal is to visit all the islands proportionally to their relative population. Okay? So that the politician spends more time on the more populated islands and less time on the less populated island. Okay, because after all, the politician only has limited amount of time, right? So when if he wants to allocate his time to different islands, okay, the island with more population obviously has a chance to get more votes, right? So he should stay there longer, okay, compared with like the islands with less population, okay? There are a few assumptions, okay, that we have to go through, okay? First, the politician has no idea what the total population of the island chain is, okay? He doesn't know the whole total population of his country. Assume he doesn't know that. Second, the politician doesn't even know exactly how many islands there are. Okay, well, you can say this politician is lazy. Okay, he doesn't even know like how many islands we have on this, in this nation. Of course, this is a made-up example. Okay, this is a made-up example. But let's assume, okay, this is the case. Okay, and the third one, the politician can ask the mayor of the island. Okay, assuming each island has a mayor, okay, or a chief, whatever you want to call it. Okay, so he can ask the mayor of the island they are on. How many people are on the island? Okay, he can ask like how many people are on the island that he's currently located. And also, when the politician proposes to visit an adjacent island, say to the island on the left, okay, he can ask the mayor of that adjacent island, how many people are on that island? So if the politician proposed to move to the left, he first asked the mayor on the island to the left, okay, how many people are on that island, and then decide whether or not to move to that island. Okay, so this is only these 5 assumptions. To be honest, like the politician really doesn't have a lot of information, right? He doesn't know the total population. He doesn't even know the number of islands, right? So how do we deal with this? Well, it's 10:54. So let's take a 10 minutes break. When we come back, okay, we will continue on this NCMC chapter. Okay, let's get started. Yeah. So we just talked about this fake example, right? I mean, it has a chain of islands, and we don't know like the total population. And for each island, if you are on the island, you can ask the population of the island. And if you decide to move to not decide, if you propose to move to one side of the island, you can ask like the population on that on the island you propose to move to. Note that this is proposed. Okay, this is proposal. This doesn't mean the politician will move to that island. This is just a proposal. Okay, I mean, depending on the population of that adjacent island, the politician will then make decision. Okay, so this is a heuristic. This heuristic is very, very simple, but interestingly, it works. It works wonder. Okay. So first, this politician flips a fair coin to decide whether or not to propose the adjacent island to the east or adjacent island to the west. So one side represents the east, one side represents the west. Okay. If the proposed island has a larger population than the current island, then the politician definitely goes to the proposed island. So for example, like after he flipped the coin, if it's the left, and the left island has more population than the current one, then the politician will go for sure. Okay. However, if the proposed island has a smaller population than the current island, then this politician goes to that proposed island only probabilistically. Okay, what do we mean by probabilistically? Okay, it means that the politician will go there. Okay, you know, proportional. Okay, the proposed island has a population as big as the current. How should I say? For example, okay, if the proposed island has a half of the population than the current island, then the probability of going there is 50%. If the population of the proposed island is 30% as the current island, then probability is going to be 30%, something like this. So if say like okay, this 30% or 50%, okay, if it turns out that the politician doesn't move, then he will stay on the current island and do this process all over again. Okay, for every day. Okay, every day. I probably should say like at the end of every day, the politician do this, decision making to see like where to move to. Okay, for the next day. Okay. So that's like try to make the last step of the heuristic to be more mathematic. Okay, let's put it as a as an equation, as a formula. Let's denote the population of the proposed island as P proposed and population of the current island as P current. So the petition only moved to the last popular island with the probability P move equal to P proposed divided by P current. So the politician does this by spinning a fair spinner mark on the circumference with uniform value from 0 to 1. I mean, this can be done like by a simple computer program very easily, right? So if the pointed to value is between 0 and the P move, then the politician move. I mean, we can do better. We can just write a program to generate a value randomly between 0 to 1. Okay, that's probably faster. Okay. Anyway, you get the idea. So let's because like in reality, we want to see like the impact of this approach. So let's intentionally let's assume the number of islands is 7 in a chain. Okay, with relative populations. Okay, proportional to the number of islands. Okay, the first island, we have 7 islands, right? So let's number these islands from 1 to 7. 1, 2, 3, 4, 5 to 7. And let's assume the first island, say, has like a 100 population. The second island has 200 population. The island 3 has 300, and so on. So the ratio is 1 to 2 to 3 to 4 to 5 to 6 to 7. Okay, just like exactly match like the number on the island. Okay, this is obviously just an example. Okay, I mean, so P parenthesis refers to a relative population of the island, just a ratio. That's good enough because I mean, we will decide to move or not based on the ratio, right? So this is not the absolute population and not its probability mass, okay? So let's see this figure. Okay, the lower figure, okay, the lowest figure represent like a 7 island and their relative population. Okay, the first island has a population of 1, second island has a population of 2, third island has a population of 3, and so on, to the 7th island has a population of 7. Okay, so now let's assume the politician start from the 4th island, the middle one. And then, okay, on the first day, the politician happens to start from the middle island, okay? And to decide where to go on the second day, he flips the coin to propose moving, okay? And in this case, the coin proposed moving right. Okay, moving right. And the island on the right-hand side has more population, right? So he definitely moved here. Okay. And then the next day, okay, the second day, okay. When t is 2 and theta is 5, I mean, theta means like where this partition is located. The coin flip proposed move to the left, okay? And the probability of accepting this proposal is, well, because like and probability move to the left, no, 0.8. Obviously, after this probability, like we decide to stay in Fifth Island for one more day. You can see we stay here longer, right? And then the third, again, we flip the coin, decide move left or move right. Now again, we move to the left. I mean, we propose to move to the left, and with the same probability, like 4 over 5, and then this time we really move to the fourth island, okay, and so on. So this shows the trajectory of the partition. And then, okay, if you accumulate the number of stay on each island, okay, for a long period of time, something interesting happens. You will see that the partition eventually stay on each island, okay, proportional to the population, the relative population of each island, right? So this, this random process, okay, even though it's we use a heuristic to decide move left or move right, okay, but eventually we are able to get more samples from the more populated place, which is the seventh island, and the fewer sample from the less populated island, which is like for example, the first island. Naturally, right? But you may argue, wait, this is just one special case, right? This is maybe just one special case. It turns out that this is always going to be the case. Not only that, okay, you may argue, well, maybe the starting point plays an important role in here, okay, because we start from the middle, right? The answer is no. No matter where you start, okay, you just are going to create such a result regardlessly where you initially you get started. So that's of course I promise you that I mean we will explain the sampling technique, okay, but at the same time I know that we are not going to really like do this like a math department, okay. So here, okay, a compromise that I'm going to do is that, okay, I'm going to show you a few arguments to convince you that this is indeed the case, okay. So how do we do it? Okay. I'm going to do two different approaches. Okay. The first one is this. Okay. This figure shows you the probability that a partition is located at the island at a certain day. Okay. We know at the day one, on the day one, partition is on the fourth island, right? So the probability for the partition on the fourth island is 100%, right? And the probability for the partition on the other islands will all be 0, right? Okay. So when T is 2 on the second day, what is the probability that the partition is located? Okay. We know like at the end of the first day, partition can flip a coin to decide move left or move right, right? If he decides to move right, because the right-hand side, the island on the right-hand side has more population, right? So he will definitely go, right? So it's going to be, because of coin flip is 50% to the right, right? So we have 0.5, okay, to that partition on the second days on the fifth island. Another possibility is that another 50%, the partition flip the coin and the result is to move to the left, okay? And the chance for this, the chance for the partition to really move to the left is 0.5 times 3/4, right? Because that's the ratio of the population, right? So the result is like, zero, no, so it's a 3 divided by 8. Well, so it's going to be somewhere near 0.4, but not exactly. I think it's 0.375 if I remember correctly, right? So there's also a chance that the partition will stay on the island 4, which is 0.5 minus 0.375, okay? And it's going to be like a little bit more than 0.1. Okay, so this is the probability where the partition will be on the day 2. Oops, sorry. And obviously, you can keep doing that, right? This is a very simple way to calculate this probability. Okay, start from the 5th island. You have like you can either move to the right or move to the left. You compute all the possibility, and from the 4th island again, you can move. The partition can move to the left or move to the right. You do all these calculations, and they add them up. So at the end of the 3rd day, the probability for partition to stay on different islands looks like this. This is the 5th day. This is 3rd day, and end of 3rd day, this is end of 4th day, end of 5th day, end of 6th day, and so on. Okay, if you use obviously, I mean, the first 2-3 days you can calculate by hand. If you want to do it like for a longer period of time, okay, you obviously should write a program. So you can see when T is like 20 12, 13, it already gives you a very good indication that it is proportional to the relative population of each island, right? But it's still not so smooth yet. If T is 99, okay, you can see it is going to be an almost exact match to a target. So this, again, let me remind you, this indicates the probability that this partition is at each island. And this happen to be proportional to the, the relative population at each island, right? So this is a very interesting observation, okay? And this obviously this is just one argument, but this is not exact proof, okay? Yeah, I think I already explained this, but so that current percent be theta current will propose to move one position right or one position left. The specific proposal is determined by flipping a coin. So probability is 50% head, 50% tail. So this range of possible proposed moves, okay, all the possible proposed move, okay, and the probability of proposing each, okay, combined is called proposal distribution. There's a, special terminology to call this. Okay, in the present algorithm, the proposal distribution is very simple because you can only move to the left adjacent island or move to the right adjacent island, each with a probability 50%. Okay. So we can also try to, write our formula a little bit better to be something like the following. Okay, P move will be mean of, P theta proposed divided by P theta current. This P indicates the relative population, okay, or 1. What do we mean by here? Okay, because we sort of like combine moving to the left and moving to the right into one single equation. Because if you move to the right, because you have more population on the right, for island on the right, right? So you will definitely move there, right? But instead of just using a, if else, we just, use this one. Okay, because like, if you put like a P theta proposed, okay, and P theta current, okay, if you propose to move to the right, okay, because the P theta proposed is larger than P theta current. So this, fraction is going to end up with a value higher than 1, right? But we know like the P move cannot, because this is a probability, right? So it cannot be higher than 1. So we just, make sure it is, upper bounded by 1. That's it. That's it. So this is actually a random walk process. Okay, random walk process. Okay, so remember I told you like this chapter is called MCMC. one MC stands for Monte Carlo. Another MC stands for like a Markov chain. Okay. What is Markov chain process? Okay. If whatever you are, I mean, this process will only be dependent to the previous status. Okay. If the next status is only dependent to the previous status, just the previous status, okay? Not the previous status, okay? Just like the previous status. And this process is called like, Markov chain, okay? And by the way, random walk is a Markov chain process. Okay, why? Because like the place you move to obviously is determined by your previous location. Okay, for example, like you are on the island 4. The only places you can go are island 3, island 5, and island 4, right? Because, well, those are either the adjacent islands or where you are located right now, right? I mean, you cannot move directly from island 4 to, for example, island 1. That's just not possible, right? So, so this is that's why this random walk. This is a Markov chain process. Okay, and for a random walk process, okay, to happen, we must have these 3 requirement. Okay, requirement. They are pretty straightforward actually. Okay, we just try to list them so that make it obvious. Okay, so first we must be able to generate a random value from the proposal distribution to create P proposed. Okay, in this example that we are talking about is that we must be able to flip the coin. Okay, I mean, of course, like in a later part, I'm going to tell you that this proposal distribution, can be more complicated. For example, it could be Gaussian. Okay, it could be uniform, by the way. But regardlessly, okay, you can always sample from Gaussian or sample from uniform distribution, right? So to sample from a given distribution is normally never a problem. Okay, so this is the first must. The second must is we must be able to generate a random value from a uniform distribution to accept or reject the proposal according to P move. Again, this is pretty straightforward. Okay, pretty straightforward. Not much that we can talk about. The third one is we must be able to generate a random value. Sorry, that's the third one. The second one is we must be able to evaluate the target distribution at any proposed position. Okay, in other words, in this example is we want to compute P theta proposed divided by P theta current. This couldn't be any easier, right? For this current example, but of course, I mean, in the later part, okay, that we are going to use this one to do the sampling, then yeah, I mean, it's normally not an issue to to evaluate the target distribution at any proposed position. Okay, this is normally never an issue. Okay, so so by being able to do these three things, okay, we are able to indirectly generate random samples from the target distribution, and this random walk technique is very, very useful when the target distribution P of theta is a posterior proportional to P D on condition of theta times P theta. Okay, we know this P theta equal this equation, right? So merely evaluating P D on condition of theta times P theta without normalizing it by P theta, P of D, okay, we don't really need to normalize it, okay, as long as we can make sure that we are generating sample that are proportional to this, you know, P of D on condition of theta times P theta, okay, or the posterior, then it's good enough. So I just told you, okay, here, okay, I will not give a formal proof, but I'm going to give two arguments, right? That why the MCMC works, okay? The first argument I gave you is this one, right? And but that one is not so strong, okay? But at least it's a circumstantial evidence, okay, to show you like you know why this approach works, okay. But now I'm going to tell you another argument, okay, and this argument combined with the previous one should give us a relatively good proof, okay, not necessarily formal either, because again, we are still considering a special case, okay, but the you know, the basic idea will be the same, okay. So let's consider two adjacent positions and the probabilities of moving from one to the other, okay. So see the relative transition probabilities between adjacent positions exactly match the relative value of the target distribution. So we can extrapolate, okay, this result across all positions. And, you know, in the long run, each position will be visited proportionally to its target value, okay. So how do we do it? Okay, it's like this. Suppose we are at position theta. The probability of moving to theta plus 1 is denoted by P of theta to theta plus 1. It's the probability of proposing that move times the probability of accepting this move, okay, if proposed, okay. So which is like, you know, P of theta to theta plus 1 is 0.5 times this one, right? This mean of P theta plus 1 divided by P theta 1. We know this from this Barton equation, right? So if we are presently at position theta plus 1, the probability of moving to theta, okay, is going to be represented by this one, right? P of theta plus 1 going to theta is 0.5 times this one. So if we try to see, okay, there are two possibilities. One is, you try to, calculate the ratio, and one, of course, because one population must be larger than the other, right? Either P of theta is larger than P of theta plus 1, or P of theta plus 1, or P of theta is smaller than P of theta plus 1. So if P of theta plus 1 larger than P theta, you put this, okay, then this one will become 1, right? The mean of this one becomes 1. And you only have this one remains. And this one will remain. So it becomes like this. And if P theta plus 1 is smaller than P theta, then this one remains. P theta plus 1 divided by P theta. And the lower one becomes 1. So it becomes this. Okay. And no matter which option you have, you're always going to end up with P theta plus 1 divided by P theta. Right? And then you can, so every adjacent position, the ratio shows something like this. Okay, so eventually, that's why, okay, you end up, the frequency will match with the population, will be proportional to the population of each island. Okay, and you could, okay, to be more specific, you can put the whole thing into a transitional matrix. Okay, so for each row, for each column, okay, represent okay, where the probability that I mean, some how should I say? I should say for each row represent from the P theta to P theta minus 1, okay, or from P theta to P theta, or from P theta to theta plus 1. Okay, you can write it like this. Okay, so then, okay, if you try to put the formula that we use in this example into this matrix, it will look something like this. And then, okay, you could use this one to calculate to obtain this one actually. Okay, initially, okay, when the partition is at the theta equal to 4, it means originally, I mean, we can represent the probability that the partition is at each item as a probability vector. And initially, because he was on item 4, so the vector is going to look like a 0, 0, 0, 1, 0, 0, 0. Okay, and if you multiply that vector, okay, to this equation, this matrix, it's going to give you the second day. Okay, I mean, where this partition is going to end up with on the second day. It's going to give you this one. In the vector form, in a vector format. And then you can apply the matrix to this vector again, and then you will get this. And you multiply matrix to a set to the vector this one, you'll get this one, and so on. So eventually, okay, you can use that transitional matrix to compute like to obtain this result. Okay, I mean, no matter where the initial point is actually. So so this is, you just formulate it as a row vector. W is a location probability into a row vector W, and then you use W multiplied by the matrix, okay, and you get like the next probability, location probabilities. So so determine the probability of the location at the next time is going to be like a W times TRC. Okay, so I already talked about this. Okay, so repeating this process will generate the graphs in slide number 16. Okay, I already told you that. So here's the interesting part. Okay, when the vector of precision probability is the target distribution, it stays that way on the next time step. Okay, so in other words, like this transition will make sure your probability distribution, the location probability vector, keep diffusing until it will stabilize. Okay, when the target, when it reach like the target precision probability that's match with the target distribution. Okay, so this is like the most important point. Okay, so yeah, I guess it's this is difficult. I mean, without going to the without using the whiteboard, it's difficult for me to show you why this is the case. Yeah, but I think we are really running out of time anyway today. So I will complete this proof next time, okay, in class. Okay, basically like okay, this one indicate like okay, you know, in the next step, you know, how this probability distribution is going to end up like. But I'm going to show you, okay, it's going to, you know, it's going to stabilize if it match with the target distribution. Okay, there are 4 cases to discuss. Okay, to be exact. So in the class, I will try to discuss at least 2. Okay, and then you can do the other 2 by yourself. Okay. Yeah, I guess like yeah, unfortunately, I mean, it's just very difficult to, even if I use whiteboard, I mean, to type those formulas like by hand is going to take too much time. So I give up. I think like it's about time that, I mean, we it's that, I mean, that it's already 11:50. So I think like we will stop today's lecture here, and I'll try to finish up this discussion next time. Okay. Yeah. So yeah, thank you for coming to the class. I will see you guys like I really hope I will see you guys in person next week. Okay. Thank you very much. Okay. Bye.